So our final 3 examples are all about hypothesis testing. That's what we did in Chapter 9, and I want us to get back and make sure we feel really confident about hypothesis testing. So let's read through the problem we're given and make some decisions and solve for some critical values and such. So a simple random sample of 50 adults. What I like to do when I'm doing a hypothesis test is go through and label everything. So a simple random sample of 50 adults, that's my N, is obtained. And each person's red blood cell count is measured. That's my variable. The sample mean, that's our X bar, is 5.23 cells per milliliter. The population standard deviation for red blood cell counts is 0.54. That's our sigma. Sigma is our population standard deviation. I want to test the claim that the sample is from a population with a mean less than 5.4 cells per milliliter. This is our claimed value, okay? This is my population mean. So the first question is, what type of test do I need to do? Do I want to use a normal distribution or a student's t-test? So first thing, I think it's important to remind ourselves, when do we use a student's t-test? We use a student's t-test when our standard deviation, so sigma, is unknown. We know our standard deviation, so this is going to be a normal distribution. That means we're going to be calculating a z-score. What are my null and alternate hypotheses? So my null hypothesis is always going to be that there's no difference from the claimed value. So it's always going to have an equal sign. My alternate hypothesis is going to be that the mean is less than, greater than, or not equal to our claimed value. So let's figure out which one we're going to have. We want to test the claim that our sample is from a population with a mean less than 5.4. Less than 5.4. That means we're using a left-tailed test. When we look at the graph of our normal distribution with a mean of 5.4 and we've got a sample mean of 5.23, our z-score is going to find the area in this tail for us. So let's go ahead and calculate this z-score. I go that z equals my sample mean minus my population mean over my standard deviation over the square root of n. So that gives me 5.23 minus 5.4 over 0.54 over the square root of my sample size, which is 50. So I get a z-score of negative 2.23. When it asks me what my critical value is, that's going to be the area under this curve right here. So I need to take my z-score, I need to look it up in a z-table, and I get a z-table value of 0.0124. That's my area over here. Next, I want us to state our conclusion, right? Well, we weren't given a significance level, so why don't we state it at both significance levels? So what would I do at the 0.05 significance level? So if 0.05 is my significance level, my p-value, or critical value, I'm going to label that as 0.0129, is less than 0.05. So if I have a 0.05 significance level, I reject my H-naught. Now, what if I have a 0.01 significance level? Well, if I have a 0.01 significance level, that means my p-value is greater than my significance level, so I do not reject my H-naught at the 0.01 significance level. So these are the two conclusions that we could come to, and both are correct. Okay, problem 11. Students randomly selected 30 people. Okay, we got a sample size. And measured the accuracy of their wristwatches. with positive arrows representing watches that were ahead of time and negative arrows representing watches that were behind the correct time, so fast or slow. The 30 values of our sample had a sample mean, right, because they're from our sample, had a mean of 117.3 seconds with a standard deviation of 185 seconds. So it's saying our 30 values had a standard deviation of 185 seconds. That's going to be an S, right? That's what we use to represent standard deviations of our sample size. We want to use it tells us we're going to use a 0.05 significance level to test the claim that the population of all watches has a mean equal to 0. So, what type of hypothesis test am I going to use? Am I going to use a normal distribution or a student's t-test? Well, I'm going to use a student's t-test, and the reason is because my standard deviation is unknown. I have the standard deviation for my sample, but not for my population. Next, what is my null and alternate hypothesis? So my null hypothesis is always there's no different from the claimed value. And my alternate hypothesis, in this case, we have to read our claim. So I want to use a 0.05 significance level to test the claim that the mean of all populations has a mean equal to 0 seconds. So since we have an equal, no hint of less than or greater than, we're going to have a two-tailed test. Oops, I gave away the next answer. Because we have does not equal. Does not equal means we have a two-tailed test. So we're going to have to find our t-score for our sample mean. So we take t equals x bar minus mu over our standard deviation over the square root of n. This is incredibly similar to our z-score equation, except we have an s instead of a sigma. I plug in my values, and I get a t-score of 3.479. Now, I need to determine the critical value for my test, and I'm going to switch colors so I can identify this well. So the critical value for my test. So I have to take some pieces of information with me. So I had my degrees of freedom, which is my sample size minus 1, so 29. I need to know my significance level, and I need to know that my test is two-tailed. So I go to the test on the t-table. I go to degrees of freedom is 29, and the area in two tails is 0.05, and I get a critical value of 2.045. Now I give you guys the rules for critical value. You want if we're doing a two-tailed test, you want your t-value to be greater than your critical value. So because our t-value is greater than our critical value, we're able to reject our h naught at the 0.05 significance level. Next, in a trial involving 1,602 children, only 14 of the 10,070 who received the vaccine developed the flu. I want to use a 0.05 significance level to test for the independence between treatment and the flu and whether or not our vaccine appears to be effective. This is a chi-square test. My null hypothesis for a chi-squared test is that there's no relationship between the variables. So there is no relationship between getting the vaccine. So relationship between treatment and flu. It's always true for chi-squares that my null hypothesis is that there's just no relationship. My alternate hypothesis is the converse of that there is a relationship between, I forgot that word there, between treatment and flu. So when we're doing a chi-squared, we find the expected value of all of our possible cells in our table, right? then we take our observed value minus our expected value, we square it, we divide it by the original expected value, we add those up for every square, and we get a chi-squared statistic, okay? In this question, I really just want you to find the expected frequency for this cell right here. So expected value is row total times column total over grand total. So that's going to be 1,056 plus 14 times, so I'm trying to find it. Oh, for the observed value of 437. Oops, I made a mathematical mistake in the homework key. So let me write this out for us, and I'm pretty sure you guys can figure it out on your own. So it's over my grand total. So I'm going to take my row total, which is 95 plus 437, times my column total, which is 1056 plus 437. I'm going to multiply those together and divide it by 1602, which was the number of people in my study. Okay, that's how you'd find the observed value, which is the question of part B. Then I want us to find the critical value for this test, okay? The critical value for this test depends on the significance level and the fact that I have a 2.2 table. So I go to the chi-squared table, which you will be given, and I look at the 0.05 significance level for a 2 by 2 table, and I find a critical value of 3.841. Now, if I want to reject my null hypothesis, I need the chi-squared statistic that I calculate to be greater than my critical value. The instructions are in the top of the chi-squared table. So if I compute my chi-square for this 2 by 2 table, I would find a test statistic of 92.7252. Okay, because 92.7 is greater than 3.841, we're rounding, we can reject our null hypothesis at the 0.05 significance level. Exclamation point, because we're really happy we're done with our exam, right? That was it. That's problem 12. This is the last problem. So I just want to wish everybody good luck and happy studying. You're going to have multiple days to work on this exam, so get it to me anytime before May 6th.